let's see how it goes. OK, so very good. So this is the title of my talk. So it's the regularity theory for area minimizing currents in codimension higher than 1. I'm going to explain actually everything, even for the people who don't have any idea what an area minimizing current is. So I should have actually put there an area minimizing integer rectifiable currents, but then it goes even to a title in 3 lines, and so I thought this is kind of ugly. OK, so the starting point is a very famous problem, which was, I think, proposed actually already by Lagrange, but it's usually referred to as a Plateaus problem in honor of a Belgian physicist who was studying essentially soap films. OK, so the problem is find the surface of least area which is spanning a given contour, and I will actually, during all the talk, think about this contour being in a Riemannian manifold, and so I'm looking for the surface which spans this contour, in the Euclidean space. But actually, all I'm going to say can be done in a Riemannian manifold, and in fact, it should be done in a Riemannian manifold because maybe the most interesting applications of what I'm going to say could potentially be in a geometric setting where you want to do this in a Riemannian manifold. So I'm going to make some comments about this. Of course, originally, the problem of Plateau was for 2-dimensional surfaces in a 3, but in fact, here we are going to consider surfaces in codimension at least higher than 1 and in general dimension. Let me fix actually some notation. So through all the talk, n is going to be OK, it's actually the other way around. M is the dimension of the surface. So you see here that my son is already perturbing the slides. So M is actually the dimension of the surface, and N is the codimension, I think. Anyway, so there are several approaches to the existence and regularity of surfaces which are minimizing the area when you fix a given contour that they should be spanning. And of course, it's a very famous problem which has a huge literature. I'm going to focus on a particular approach which has a lot of geometric features, and it's the approach of Federer and Inflaming through the theory of integer rectifiable currents. And this theory generalizes a previous theory which existed in codimension 1, which is the George's theory of sets of finite perimeter. OK, one should mention that there are actually several other approaches. I mean, for instance, Reifenberg approach or Douglas-Rado, which actually came before. I'm not going to actually consider any of these other approaches. There is no particular reason for doing this. Of course, depending on which problem you want to solve, these different approaches actually, they have different features. So for instance, if you're really interested in the geometry of soap films, probably in 2 dimensions in R3, there are some phenomena that the theory of currents are not going to capture. Anyhow, so what is a current? So we go back to de Rham, actually, who was, I think, the first one to define a current. So for us, a current is an n-dimensional current is just a linear map on the space of smooth forms. OK, so we have a smooth form omega, and the current just gives us a number, a real number. OK, of course, we recover the classical C1-oriented surfaces via simple integration. OK, so you have a smooth form, you integrate over your manifold, and that is going to give you a number. And you think of this action as actually essentially identifying your smooth-oriented surface. OK, so this actually is it's a very nice idea because in some sense you can take Stokes' theorem and use it as a definition of a boundary of a current. So if you have a general current T, its boundary is going to have 1 dimension less, and you have to define its action on n-1 forms. And what you do is you essentially enforce Stokes' theorem. And of course, Stokes' theorem is just telling you that this is compatible with the usual notion of boundary that you have for classical surfaces. OK, it's a bit more complicated to explain that there is a very natural generalization of what is the volume, then, of a current. So you can think about the volume of a manifold as essentially the maximum of this integral that you can get if your form is less or equal than 1. So for instance, if you're looking at the length of a curve, right? So the length of a curve can be characterized as the supremum of the integral over the curve of vector fields which have length less or equal than 1. So something similar can be done for the current, only you have to just adjust exactly what you understand by the mass, or what is called actually the co-mass of the form omega to be less or equal than 1, and I'm not going to give you the precise definition. Anyhow, once you have actually this setting, you could simply say, OK, so I give you an n-1 dimensional boundary in the Euclidean space, which is as a closed submanifold, oriented submanifold. It bounds some classical surface. And then I can look at all currents which bound this contour. and minimize the mass, which I just defined, which generalizes the volume. It's actually very easy to show then that there exists a minimizer in this context. It's very easy because it's going to be essentially basic functional analysis. So you are in a linear space. You actually have a functional which is defined on the linear space, and it's convex. You have enough compactness by abstract theory, and there's a minimizer. So this actually, anyhow, has at least one problem, one drawback. So you are allowing, by this mechanism, to take, for instance, a surface and put a multiplicity 1/2 on this surface. I mean, this defines you an integral. I mean, you just get to take half of the integral which is given on the surface. So it might be that the minimizer is 1/2 of a surface. It might be actually that the minimizer is a real coefficient time a surface. There actually might be much worse situations in which, for instance, your general current cannot even be identified as a surface with a certain density on it, but it could be, for instance, a one-parameter family of surfaces, and you can kind of spread the density in a continuous way over this foliation, I mean, for instance. OK, this is not very desirable, and to sort of cure this disease, if you want, Federer and Fleming in the 60s, they introduced the theory of integer rectifiable currents. So how are you going to define integer rectifiable currents? So I mean, this is maybe a little ugly as a definition, although I think it's the best that you could find in the literature. In fact, since geometric measure theorists have some masochistic attitude at giving very complicated definitions, I think you will find definitions in the literature which are way worse than this. So anyhow, think about having a countable collection of C1-oriented surfaces. Now, on each of these surfaces, you actually pick a compact subset. The compact subset might be very bad. So for instance, you can take a plane, and you can cut out a square inside, and that's OK. But you can also cut out somehow a set which is very porous, for instance. OK, so you then choose, OK, so you choose these joint compact sets. I mean, let me stress on this. And then you choose actually positive integers. And you require that your choice gives you that this series is bounded. OK, then you can define a current as the formal union of ki times all these pieces. And of course, to be consistent with the definition, I have to tell you what is the action of this current on a form. And what I do is I simply integrate over each piece the current omega. So here, I obviously forgot actually to take ki, which is a positive integer. So I should multiply then this integral by ki, sorry. And then I sum all the result. And this is going to give you a linear functional. This is going to give you a well-defined number, because I'm assuming that this quantity here is finite. So this series is actually converging. So remember that here, there should be a coefficient ki, which I forgot, which is the multiplicity with which you consider that particular surface. OK, so that defines you an integer rectifiable current. And of course, now you could simply say, OK, so I know what an integer rectifiable current is. I know what its mass is. Actually, I gave you the abstract definition. But if you work out the definition, in this case, this quantity, which is finite, is exactly the mass of the current. So it's exactly the total volume of the current, as you intuitively expect. You can now try to minimize the area among these objects. OK, this turns out to be way much more difficult than what I told you at the beginning. So this is, in a nutshell, the Federer-Fleming theory. So the theory of Federer and Fleming in the paper, in the foundational paper in the 1960s. So this time, your objects that are the integer rectifiable currents, they are not anymore a linear space, right? Because I cannot take any linear combination of currents with real coefficients. I can only take integer combinations, because otherwise the coefficients wouldn't stay in integral, right? Which is what I hopefully said here, right? So this time is not anymore linear function analysis, and it's actually a very hard theorem to prove that you have enough compactness to minimize and to have a minimizer of the Plateau problem in this context. OK, so this is the context of what is called the Federer and Fleming compactness theory. As a corollary, you actually achieve an existence of an area minimizing current for any smooth boundary that you actually can impose in Rn plus 1 in the Euclidean space. There is another very important point of the theory, which is the so-called deformation lemma. So the deformation lemma is an approximation procedure of any integer rectifiable current with a sequence of more or less smooth surfaces, okay? Or at least with finite, linear finite combination of smooth surfaces with integer multiplicities. I'm not going through I cannot state it to you because it's going to be very technical, but there is one corollary of this deformation lemma. This corollary tells you if in the class of smooth surfaces you have a minimizer in that particular class, this is going to be a minimizer even in the integer rectifiable class. So if you have a smooth object which is solving the Plateaus problem in the class of smooth objects, then the integer rectifiable currents theory will give you that. So if the integer rectifiable currents theory gives you only singular objects, then there's not going to be a minimizer in the class of smooth objects. Okay? Very good. So this does not happen for a lot of other theories. For instance, it doesn't happen for Reifenberg theory, if you want. OK, so there's another very important feature. I don't think I have to explain it in this audience. So this is an homological theory. So for instance, one thing that you can do with this theory is just to say, if you are in a Riemannian manifold, pick up in a compact Riemannian manifold, pick up pick up an homology class. The homology class will be always represented by an integer rectifiable currents which minimizes the area. There will always be a canonical representative. And that is, of course, very nice for potential geometric and topological applications. OK, now, of course, a general integer rectifiable current might be very non-smooth because you can simply take random pieces of surfaces and patch them together. So the first question that you ask is, how regular is this going to be? And the literature has an almost complete answer to this problem already at the beginning of the 80s. OK, so it was a fantastic achievement in the 60s or 70s of several people. I hope I'm not forgetting anybody. So I think the story starts with the Georgi. It's not only because he's the advisor of my advisor. I mean, I really will show you that it starts with him. And it ends essentially with Simons. Although there's a very, very important later contribution by Leon Simon, which I'm going to tell you. So if you are looking at hypersurfaces which are area minimizing currents, then these are classical smooth submanifolds, except for a possible singular set. And the singular set has codimension 7 in the current. OK, it seems I'm actually consistent with my initial notation. OK, so this singular set, which we will show in a moment, actually does exist, is even rectifiable. And this was a fantastic achievement by Leon Simon at the beginning of the 90s, I think. OK, in higher codimension, the situation is rather different. That is, the singular set might have codimension 2 in the current. And I mean, this result is credited only to Almgren because essentially it was really proved only by him. And a proof appeared at the beginning of the 80s. OK, now I don't have to say it here somehow. The codimension 1 result has a huge amount of applications in geometric problems. And the reason for this, some of the people here are the founders of many spectacular achievements that you can actually do with minimus hypersurfaces in the study of geometry and topology of manifolds. The codimension bigger than 1 result has, I would say, much less repercussions. I mean, there's actually a beautiful paper of Taubes that ignited a lot of interest in the regularity theory of Almgren because he used actually a particular case. He reproved, in fact, a particular case that he was using of this regularity theory to prove the equivalence of Gromov and Seiberg-Bigden invariance. Anyhow, so one of the problems with the codimension bigger than 1 result is that originally it was a manuscript of 1,700 typewritten pages. Actually, I think it was 1,728, to be precise. Now, with TeX, you can actually compress this. And this was done by Vladimir Scheffer and Gene Taylor. And you arrive to a really pretty bulky book of 1,000 pages. I mean, OK, sure, it's 1,000 pages, but the font is pretty small. And the page is pretty large. Now, OK, so my opinion is that, it's also not only that somehow, for instance, Theorem 1, this theorem over here was very influential in the literature because you can use it as a black box. It's not only that. It's that once people really digested and understood the proof, right? I mean, they actually modified the proof to build a regularity theory in several other situations. And this was extremely successful. I mean, think only about, for instance, the regularity theory that was initiated by Schoen-Simon Yao for stable minimal hypersurfaces. Of course, if you have a proof of 1,700 pages, then it's rather difficult to try to sort of adapt it to different contexts. OK, so it was, OK, so maybe before coming to that, let me just tell you this very important thing. So the result is optimal. I mean, both in Codimension 1 and in higher Codimension, the result is optimal. So in Codimension 1, the first famous example of a singular area minimizing currents is the Simon's cone, for which I give you here the expression. It's a 7-dimensional surfaces in R8. So it was pointed out by Simons that this is a stable minimal hypersurface, but it was proved then by Bombieri, De Giorgi, and Giusti that this is really a minimizing of the area. So and this has a singular point. So there is a codimension 7 singularity. The situation is, for counterexamples, of course, the situation is much easier in higher codimension. So if you are in higher codimension, you have this powerful theorem by Federer, which builds on an inequality of Wirtinger, which tells you anytime you have an holomorphic submanifolds of a Kähler manifold, this actually gives you an area minimizing current. I mean, for instance, it gives you a minimizer if you just make compactly supported perturbation of it, right, in CN. So, of course, holomorphic submanifolds or even algebraic subvarieties are the most regular objects that we can think about. But from the point of view, I mean, from a geometric or topological point of view, of course, they have singularities, meaning they have points where they cannot be written as they cannot be written as the graph of a function. OK, and they typically have real codimension 2, these points. OK, so let me actually, for later purposes, give you 2 examples which are going to be extremely important. So there is one guy which I call the bad guy. So it's this algebraic subvariety of C2. I mean, in complex coordinates, it's just z squared equal to w to the power 3. I mean, in the origin, it's not possible to write this as the graph of a single-valued function, right? So either you pick up one coordinate and you will have a 3 covering of a plane, or you pick up the other coordinates and then you will have a 2 covering, OK? So and typically, you would pick up the coordinate in which you have z equal w to the 3 over 2, and then you have the 2 square roots of the complex number. But the really bad guy, I will tell you in a moment why it's really bad. It's actually something like this. So in principle, the singularity is given by, I mean, if you remove this w to the power 2, the singularity is something like z goes into w to the 2014 divided by 3. But remember that we have this w squared over here, which is going to play a huge role in what follows. OK, so after a few years of effort, I think I started actually studying this problem maybe back in 2004 when I was a postdoc of Tristan Rivière at ETH. So maybe it was even the end of 2003. So together with a former PhD student of mine, we actually could produce a shorter and, we hope, much more readable proof of Almgren's theorem. So some things are really the same. And I'm going to explain you that we still use the program of Almgren, so his main approach, and some of his core ideas. In particular, remember this frequency function keyword. But we introduce some new techniques of which we take advantage. And I mean, these new techniques actually didn't exist at the time of Almgren, but we realized that we can use it to get a better understanding. We introduced some new ideas, which are not only new techniques, but really some new ideas that we had. And as, of course, as a hard analyst, you also have to show that there is some new estimate. Otherwise, it's a kind of, I mean, for a hard analyst, if you don't prove at least some new hard estimate, then, I mean, your colleagues are going to think you're a wimp, in a sense. OK. So, and hopefully, unfortunately, I'm not able to announce the theorems now because we are writing down the proofs. But the hope was, of course, to go beyond Almgren's theory and to show that, you can use some of his ideas and prove actually some theorems which are not contained in his big book. And this is what unfortunately, I cannot do right now, but hopefully in 2 or 3 months, once we have finished writing the paper. OK, so let me give you an idea now of the following. So how you can prove actually Almgren's regularity result. And what are the new contributions that, I mean, the new inputs that we have in our papers? Of course, this is going to be very sketchy, but still, I think it's the most interesting. I mean, it would be very interesting if I can at least convey you some of the ideas which are inside. OK, so there is a step 0. So I will actually break Almgren's program essentially in 4 main steps. OK, But there is a first step, which I call step 0. The reason why I call step 0 is that it's actually an effect of 5 pages of his book. And it's an effect of 5 pages of his book, which penetrated the literature right away. OK. So you have to think about the following effect. So if you have a smooth surface and you take a point on the smooth surface and you start rescaling the surface homothetically around this point, in the limit, you get a tangent plane. Right? I mean, this is a manifestation of the regularity of the surface. So you can ask whether something like this happens also for an integratifiable current. OK. So now the type of convergence which I will take is not the convergence of the smooth manifold, which would be uniformly or C infinity or Cj, whatever. It's a much weaker convergence. On the other hand, when I rescale a current in a certain point, and for some subsequence, unfortunately, the limit of the rescaling might depend on the subsequences as far as we know, since the uniqueness of the limiting object is a big open problem. So if the limiting object is going to be a flat plane, maybe counted with a multiplicity which is larger than 1, I will call this flat plane a weak tangent. OK? So now, OK, so here I wrote quite a lot of stuff, but let me just summarize this slide in the following way. So out of some measured theoretic arguments, you know that at most points, when you are rescaling, you are finding, in the limit, a flat tangent plane. Why is that? So at a very low level, it's a little bit like telling you if you have an L1 function and you rescale an L1 function around one point, you're converging to a constant, which is the Lebesgue, which is going to happen in the Lebesgue point. So this happens for a normal function almost everywhere. And for an integratifiable current, it happens almost everywhere. Actually, being an area minimizing current improves this situation and tells you that something like that happens outside of a set of codimension 2. And OK, so this is proved in Almgren's paper. As I told you, it's something which penetrated in the literature, and it's called Almgren's stratification theorem. It's actually a corollary of the Almgren stratification theorem. So somehow, in some sense, one of the starting points would be that on a point when I have a weak tangent, I hope to prove regularity for my surface. OK, now let me stress that you might actually pick up, when you do this rescaling, a tangent plane with higher multiplicity, although your initial surface had multiplicity 1. So if you think about the bad example, so if you take that holomorphic curve with multiplicity 1, when you do this zooming procedure in the singularity, you will see in the limit 2 copies of the plane z equals 0, of the complex plane z equals 0. So although the initial algebraic surface had multiplicity 1. OK, so now let me tell you what happens in codimension 1. So in codimension 1, de Giorgi observed, well, observed maybe is a bad word somehow. De Giorgi proved that as soon as you have one weak tangent which is flat, you're actually regular around this point. And this is maybe the first epsilon regularity theorem that you find in a geometric analysis problem. I mean, maybe not. It's surely one of the very first. OK, so actually, de Giorgi's theorem is exactly telling you if your area minimizing current in codimension 1 is sufficiently close to a plane in a weak sense in the ball of radius 1, in the ball of radius 1/2, it will be a smooth surface, actually a C1 alpha surface, and then higher smoothness is just coming from PDEs. Now, Almgren in the 60s immediately generalized this to higher codimension, but there is a big problem. So in higher codimension, the theorem is still true, but only under the assumption that the plane to which you're close has multiplicity 1. And in fact, I'm going to actually call this theorem essentially Allard's theorem. And the reason is because Allard gave a very powerful generalization to stationary varifolds, to stationary objects slightly after, in the 70s. And this has played an enormous role in the literature. OK, so what is actually the core of de Giorgi's idea? Let me give you a brief explanation. So assume a priori you know that your surface is the graph of a function. OK? So you can look at the area functional now in the graphical coordinates, and you can express it as an integral over the domain over which your surface is a graph. So actually, the area function is going to be the square root of 1 plus the gradient of f squared. So this is the Hilbert-Schmidt norm. And then you have sum of squares of all the minors, which are at least 4th order in the gradient of f. When you make a Taylor expansion, you will find, of course, the constant 1, the Dirichlet energy, and then higher order terms. OK, so this gives you the following intuition. If you are a minimizer of the area functional, you are then maybe very close to be a minimizer of the Dirichlet functional. Now, a minimizer of the Dirichlet function is an harmonic function. Harmonic functions have very strong integral decay properties. And what you could hope is to lift some of these integral decay properties to the current. I mean, because they are integrals, and somehow the current is defined by integration. If you would be able to do so, you could hope to prove that some quantities decay and then use some Murray-type lemmas and prove regularity for your surface. And that's what actually the Giorgi does. So the quantity that decays, it's called excess. I'm not going to explain you exactly what it is, but it measures the flatness of the current. So it measures the distance to a flat tangent plane. So the Giorgi's theorem is essentially telling you the following. If at a certain scale you're flat, this flatness improves when you go to smaller scales and improves in a geometric fashion, which is going to give you a C1 alpha estimate. OK, so now when you look at this, you immediately see why the bad guy is bad. So you see, when you are around 0, 0, your bad guy, which is z equal w to the 3 over 2, has very flat tangent planes. So to all purposes, if you don't know that you are two-valued, I mean, if you're locally in a portion of this surface and you look at your tangent plane is almost horizontal. And of course, in an integral sense, this is very small. Nonetheless, there is no regularity around the point 0. So you're never going to have that this is a regular submanifold. So this epsilon regularity theory of the Giorgi fails in higher codimension as soon as you don't know that, as soon as you're not sure that the flat plane to which you're close is picked up with multiplicity 1. So it's a combination of higher multiplicity and higher codimension which is killing you in this case. The situation is even worse in a sense because you cannot really hope for a decay of the excess. So if you take something like this, so z is equal to the square root of w times epsilon, right? If you take the epsilon very small, you start off at scale 1 with something which is very flat. The flatness is not improving until you go at scale epsilon, right? And the tangent has almost completely tilted to becoming vertical. And then, of course, from scale epsilon to scale epsilon squared and so on, the flatness is improving because you're getting closer and closer to w equals z squared divided by epsilon, right? So, and you kill eventually the epsilon when the z is sufficiently small. So you cannot hope for any excess decay in higher codimension as soon as you have multiplicity higher than 1. So in this sense, the Allard's theorem is optimal, even in higher codimension. So how are you going to deal with this? Because essentially what we are saying is that there is no epsilon regularity theory that you could hope for. So, OK, so this actually gives you step 1 of Almgren's program. So the idea is, OK, so around the singularity of, for instance, the bad guy, I cannot approximate my current with a single-valued map. It's not a single-valued map. It's not the graph of a single-valued map. But it's the graph of a multiple-valued map. So one of the questions that you can pose yourself is, can I build a linear theory? So can I build a theory of maps taking more than one values and minimizing the Dirichlet integral? So can I define Sobolev spaces? Can I prove that there exists a minimizer? Can I prove regularity for this minimizer? And the answer of Almgren is really beautiful. So in the first fifth of his book, he proves that you can define Sobolev maps taking more than one values with a geometrically meaningful definition of Dirichlet energy. Of course, if I define the Dirichlet energy to be stupid, to be identically equal to 0, then I get a trivial theory. So I want the Dirichlet energy that I can spend in a geometric problem. And the spectacular achievement is the second theorem, which gives you a regularity theory for the minimizers of the Dirichlet energy, which is almost optimal, actually. So the minimizer is going to be a continuous function, and it's going to be regular outside of a set of codimension 2. So what do I mean by regular? So by regular, I mean that outside of some points, locally, your minimizer must be the superpositions of single harmonic functions. And not only it's the superposition of single harmonic functions. These single harmonic functions or these single-valued harmonic graphs cannot intersect. So either they are disjoint or they completely collapse. Of course, you could have one single harmonic function with a multiplicity q, for instance. But then it's a complete collapsing. So the harmonic sheets must ignore each other. If they cross, then they just completely touch. OK? Very good. So OK, so what's new in our approach to this? I mean, we have a much shorter proof of both theorems. What are we doing, actually, which is new with respect to him? So we take advantage of some things which actually came later. And it's a metric analysis point of view, if you want, or a metric geometry point of view. Now, so this, of course, is just, in some sense, a soft idea. On the other hand, it gives you a lot of advantage in recognizing which steps of an eventual proof might have a hard part and which steps, actually, they're going to be easy. I mean, if you pick Almgren's book, there will be a huge amount of combinatorial arguments. And actually, what you can realize by using these techniques is that a lot of these combinatorial arguments are completely unnecessary. I mean, you can kill them by simply abstract arguments if you want. And then when it actually boils down to the important part, you will really have to do with the combinatorics. This is going to be actually a small portion on which you can focus. I mean, it's not the only effect. I will show you in later steps that we can combine this with a more recent theory, which is very efficient, which I will call the metric theory of currents, which is essentially due to Gerard Sonner, Ambrosio Kirchheim, and White. And this will have a lot of features when you go on in the proof of the in the proof of the regularity. So we also have a couple of new things that we can do which are not present in Almgren, and these are really hard analysis theorems. So for instance, we can prove a higher integrability of the gradient of a minimizer, which apparently he didn't notice. At least I don't find it in the book. And actually, a student of mine extended the continuity result up to the boundary, building upon our work. So the continuity of Almgren is only in the interior. OK, so now a very important point is what is triggering actually this regularity theorem outside of the singular points? So there is a quantity which is called the frequency function. It's very famous in the literature. So it's this quantity here. The basic observation of Almgren is that even if you are in a classical setting, even if you have a classical harmonic function, this quantity over here is monotone in R. Once it is monotone in R, it's actually increasing in R. So if you go from R equal 1 to 0, this quantity is actually decreasing. In particular, it's bounded. Now, if you apply it to a classical harmonic function, you will discover a very beautiful thing. This quantity in the limit picks up a constant multiple. The constant will depend only on the dimension of the degree of the first non-trivial harmonic polynomial in the Taylor expansion of the function. Okay? So it gives you the order of contact or the order of vanishing of an harmonic function, right? So an harmonic function is analytic, therefore it must have a finite order of contact with a constant 0. But what is the order of contact is actually given by the limit of this quantity. OK, so this has two effects. So first of all, the order of contact is finite, which tells you by a suitable rescaling, I can find the best first-order approximation in the Taylor expansion to my function. So I can take this as a model of my function. But it also has a second effect. Since the quantity is monotone, when you look actually the final guy, you will discover that for the final guy, this frequency function has to be constant. And this will tell you that the model, I mean, the thing that you can extract by a simple compactness argument is going to be an homogeneous polynomial. Okay, so now when you do it for the classical functions, you just discover that, OK, so you just get the first non-trivial term in the Taylor expansion. It's not interesting. But when you do it in multiple valued functions, you actually discover that you have a model for your function at that point. And the model is giving you a first approximation with a function which is homogeneous. Now, if you think about being in 2 dimensions, once the function is homogeneous and it's minimizing a certain quantity, you actually reduce to a minimization of a functional in 1 variable. So you actually finally study an ODE, which means that in 2 dimensions, you can actually study the blow-ups, if you want, which you gain by this monotonicity of the frequency function. And you can classify them. And once you classify them, you discover the following very important point. If 0 is a singularity, I mean, if the point where you are scaling is a singularity for the limit, then the sheets of this function have to separate. And once the sheets of the function separate, for instance, if you are in a 2-valued setting, say, then you have to be regular outside of this point. So you gain regularity except for the very point where you are singular. Of course, what you hope to do now is to use this information to say that, OK, so if I have a singular point at a certain, I mean, if some point is singular out of this blow-up argument, I maybe hope to prove that actually my multiple valued harmonic function is regular outside of the punctured ball. Okay, and this is, in essence, Almgren strategy. So what's actually new in our papers? So there is one very important observation which will play a huge role later. So you see, the frequency function is slightly singular, and the reason why it's singular is that you're integrating here over the sphere. Actually, the singular, the frequency function, and this seems to be not observed in the literature, is just a limit of a smooth family of frequency functions, which are all monotone in the case of harmonic functions. So you just pick up any function phi, you smooth it. Actually, here there's a mistake. It's not phi prime. It has to be divided by modulus of x. OK, never mind about that. But these smoothed objects have a denominator which is not an integral over a sphere. It's still a bulk integral. And this is going to play a huge role later. OK, so very good. So now we actually have, out of this first linear theory, a first plan to prove regularity. So the plan would be the following. So assume, for instance, you are two-valued in your current. The multiplicity is everywhere 2. So you know by step 0 that there must be a lot of places where the current is very flat. Assume you have a lot of singularities. So these singularities must be multiple 2 points, because where the point has multiplicity 1, you know by Allard's theory that actually that has to be regular. So how can you have many singularities? You can have many singularities if you have many multiplicity 2 points, which are surrounded by multiplicity 1 points. Because if you have a multiplicity 2 points, which is only surrounded by multiplicity 2 points, you can divide by 2 and get an integratifiable current, which is minimizing and which is with multiplicity 1, and then apply Allard again. So a situation for a singularity is a situation like where you have the bad guy, but the branchings of the bad guy is really repeated in many, 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 many points. Now, if you have many singular points, what happens is that they have to accumulate somewhere. And hopefully, they are going to accumulate in some points where you also know there is a flat tangent plane. OK, so that you can prove out of abstract measure theoretic setting. So now the idea would be, once you have a sequence of singularities, for instance, which is clustering towards one singularity here, and the current is very flat here, I try to approximate my current with a multiple-valued harmonic function, and I try to prove that the multiple-valued harmonic function inherits all the singularities. That would contradict the regularity theory for harmonic functions, because an harmonic function cannot have too many singularities. So the plan is roughly the following. The plan is to approximate your current with an harmonic multiple-valued function and show that if the current is too singular, the approximation inherits all the singularities. And then you contradict the regularity theory of the linear theory. OK, so this gives you a very important point. To carry on this plan, you have to understand how to approximate efficiently a current with a multiple-valued function. OK, so this we could call step 2 of the Almgren's program. So approximate any area minimizing current with a Lipschitz map which takes Q values. And Q is dictated by the multiplicity of the flat plane to which you are close. Okay? So you are in a situation in which you're almost flat. OK, so we carry on this plan in a rather different way compared to what is actually done in the literature usually. So we use this metric approach, which I told you, in combination with the theory of Ambrosio and Kirchheim of metric currents. And there is a new estimate which allows you to apply standard techniques to approximate Sobolev functions in an abstract setting. And this will translate into a Q-valued approximation. So I don't have actually any time to tell you what this does, but there is an important point. If you compare it to the usual approximation strategies, it gives you much more accurate estimates on how good your approximation is. So typically, your approximation is something like this. You have a current which is almost flat. It will coincide with the graph of a Q-valued function, except for a set of small measure. And the approximation will be Lipschitz. And now you actually want to know how big is the measure of the set where you miss the current compared to how big is the Lipschitz constant. And typically, you would like to keep both the Lipschitz constant small and the sides of the bad set where you don't have coincidence between the graph of the current small. And this approach gives you much better estimates. OK, now, unfortunately, if you look at the plan, it fails miserably. And it fails miserably on this very bad guy that I told you. Why it fails miserably? So if you look at this guy, right, this is something like W is equal Z squared plus 3 roots of W to the power 2014. So it's essentially W equals Z squared plus a very, very, very tiny deviation from it, which is a 3-valued deviation, which is a branching singularity, but it's really tiny. If you are going to zoom into the singularity without modding out the W square, you will never see the W to the power 2014 divided by 3, which is the singular guy. And of course, you might be able, by a very fancy argument, to capture the 2014 divided by 3 approximation, but maybe the singularity was 2,000,014. So you actually don't know how little is the branching singularity compared to the regular part. So the point here is that the singular behavior is a very high-order perturbation. Again, you cannot capture it out of an epsilon regularity theorem. So, OK, this is really not a technical point. So if you look into Almgren's book, what I told you up to now, it's 1/4 of the proof. So the remaining 750 pages are actually meant to deal only with this problem, essentially. So although you actually did a lot of work, you are not even halfway through the proof. OK, it's a bit better with our approach, because in our papers, you would be almost at half of the proof at least. But still. So now, what's the idea? So why is this problem here not creating troubles at the level of the linear theory? It's not creating troubles at the level of the linear theory. It's for the following reason. So assume you have a situation like this in which the multiple sheets are actually locally harmonic functions. You will notice in this case that this Z square is actually the average of the 3 sheets. And the average of harmonic functions is harmonic. So what you can do in the case of harmonic functions, you can take the average of the sheets for the multiple valued function and subtract it. And now the average would be equal to 0. So this tells you around the singular point, the regular part is completely trivial. And the first order approximation, the first non-trivial expansion in your Taylor or fancy Taylor expansion must to be singular, because the regularity is always going to be collapsed to 0. So, OK, this is what you can do. In a linear case, you can subtract the average of the sheets. Now, you would like to do something like this here as well for the area minimizing currents. I mean, for instance, in that case, what you would like to say is, OK, so W equals Z squared is the average of the sheets. So let us subtract it. Now, you can do it in that particular case because that is not only an area minimizing current, it's an algebraic subvariety. So there is a linear structure in the Cauchy-Riemann equations which allows you to do that. But now the equation of mean curvature equal to 0, or anyhow the problem of minimizing the area, is a nonlinear problem. So if you take the average of functions which are satisfying the minima surface equation, no way this is going to satisfy the minima surface equation. Of course, a priori, you have an even more puzzling problem. You don't know that you are a multiple valued graph from the start, because that would be a very strong regularity assumption already. So the idea would be that, in some sense, you would like to construct an average of the surface, which you cannot construct literally to be the average. So you want to approximate the average of the surface. And you want to have 2 things. So you want to have the surface to be sufficiently smooth to carry on some computations. We will see in a moment. And this to be very close to the average, which maybe a priori is very singular, because you don't have any PDE for it. OK, so in Italy, it's a situation where we say you want your wife drunk and the bottle of wine full. So let me make one important point. So once you have actually identified the center manifold, so this would be step 3 in Almgren program, you now want to subtract it. But you cannot subtract it. Why you cannot subtract it? Because if you subtract and you try a Taylor expansion of what remains, the remaining multiple valued function is not going to minimize the area, the Dirichlet energy. It's going to minimize an ugly functional, which is maybe quadratic, but which will depend on the thing that you have subtracted. So if you want to make an accurate Taylor expansion of your current, you actually should do the following. You should reapproximate your current on the normal bundle of your center manifold. Let us look at the following model problem. So say that you have a manifold M, and say that you have a classical map, which is taking values on the normal bundle to this. So of course, I'm always thinking about this manifold to be in the Euclidean space, and of course, the normal bundle, which is parameterized a tubular neighborhood. So let us take the surface, which is the perturbation of your manifold M. So it's X plus you move in the normal direction a little bit. So what is the Taylor expansion of the volume? OK, so the volume is going to be not the volume of sigma, of course. So here there is the volume of M. Then there is going to be the linear part, which is the mean curvature of M times the normal displacement. Then there is the guy you like, which is the Dirichlet energy, really. Actually, there's a factor 1/2 missing. And then there is a quadratic functional, and then there are higher order terms. Now, H is the mean curvature, and Q is a quadratic form which depends on the second fundamental form of M. Now, if you are in a situation where you are very, very flat, the second fundamental form of your average is hopefully small. So this is going to be bounded by a small constant times n squared. So at all effects, you would like this to be the dominating term of the functional, but you have this linear. And of course, you cannot neglect a linear term in a Taylor expansion and make the quadratic win. Well, in your case, though, you are multiple valued, not only one valued. And your center manifold should be more or less the average of the sheets. So what you can hope is that when you carry on the computation for a multiple sheeted situation, you get that the linear term is Q, the number of values, times this integral, where I don't multiply by a single valued function, but I multiply by the average of the values over a single point. And this average should be 0, because your manifold is more or less almost the average of the current. I mean, more or less almost the average of the sheets. So OK, so now you understand what you want from this center manifold. So it has to be at least C2 to carry on these computations, because I mean, I need to approximate from the normal bundle. So it needs to be almost C2. Actually, when you go further to step 4, which will come in a few minutes, very briefly, so you realize that you have to take first variations. So you will actually need C3 regularity, because you will compute derivatives of the second fundamental form also. And then you want another very important point. So the center manifold must be very, very close to the average of the sheets. Now, you can make a Gedanken experiment, which is the following. So assume your manifold, your current, is extremely regular, and you know you are lucky. It's actually Q times a minimal surface. Assume you know it. Then your average should better be your minimal surface. And you are not allowed any mistake, because dn squared is never going to win compared to a displacement which is not exactly averaged. So this tells you the following. So you're hoping for an algorithm which is going to give you this center manifold that, if you apply to the old problem of de Giorgi or Allard's theorem, is going to give you direct C3 regularity without passing through Schauder estimates. OK? So de Giorgi gives you C1 alpha, and then use Schauder, or Allard gives you C1 alpha, and then you use Schauder to get C infinity. So here you hope to get C3 directly. OK, so this is actually noticed by Algren. I mean, Algren says the following in the introduction. So go at the end of chapter 4, which is almost 9/10 of the book. You will discover the following funny thing. I can prove directly C3 alpha regularity for a minima surface without passing through Schauder estimates, out of elementary arguments. OK, so this was our starting point to understand actually how this is possible. And it is indeed possible to prove directly C3 alpha with a short elementary proof. OK, so short elementary proof means 15 pages and knowledge of the usual stuff. I mean, what was done in the 50s and the 60s. I mean, without adding too many. I mean, without adding too new technology. OK, so now you actually have an important point. So if you actually now want to perform the step 3, you realize that going back to step 2, the approximation that you started with was not good enough. So you need a much better approximation. I'm not going to tell you exactly what this is. So you need much better estimates in the accuracy of the approximation. So, OK, so this is actually very hard in Almgren's book. And I don't quite understand how he does it. So we have an important new estimates here. So we prove this higher integrability of the gradient of harmonic functions, which is, in some sense, a reverse Hölder inequality. And this allows us to cut out a big chunk of his proof. So, and this is another important point in step 2. OK, so now back to step 3. Now, the center manifold is essentially constructed out of this idea. So locally, where you are flat, you know that you can approximate your current with a multiple valued function, which is almost harmonic. So what you will do is the following. So you fix, I mean, here's a long explanation, but you fix a point. You know that you start off at some scale that you are very flat. You know maybe that there is one scale at which you're not flat anymore. This is what happens, for instance, in the bad example. So you pick up the first scale in which you start not being flat anymore. You approximate your current with a multiple valued function, and you take the average of the approximation. This gives you a local approximation which is good. The only problem is that depending on which point you are, you might get a completely different approximation. So for instance, the coordinates might have tilted. The function might look very different. OK, so in some way, what you want to do is to patch all these local approximations which are different into a single manifold and hope that this single manifold is going to be C3 alpha. OK, so this is what we do. And this is apparently what also Almgren does. Of course, you could ask what is new in this case. And now at this point, embarrassingly, I wouldn't be able to really tell you what is new, because I cannot follow his argument. So his construction of the center manifold is 500 to 600 pages, and our construction is 50 to 60. And if you look at his introduction, what he's doing is what I'm telling you. And if you look at our introduction, what we are doing is what I'm telling you. But then why actually our proof is much shorter, I cannot really say. So maybe there is at least one thing that I can say. So the last approximation step is for him very cumbersome because he reproves an approximation from the start. We actually don't do this. So we use the graphical approximation with which we constructed the center manifold. And then we change, I mean, we reparameterize it by changing coordinates. I mean, this gives you at the first sight a very ugly reparameterization theorem, which looks almost desperate, but actually is not that difficult given the technology that we introduced in step 1 and step 2. So it's pretty quick. And once you have this, you essentially discover that all the work you did in step 2, you can recycle in step 3. And the approximation, the new approximation is going to be an easy consequence. OK, so now let me skip this. Let me even skip the splitting before tilting, and let me just get to the final step. So what would you like to do now? So you would like to implement the plan, which I told you, but on the approximation that you had on the normal bundle of this center manifold. Now you don't have the problem anymore that you had with the very bad example long ago. So if you go back, somehow you have to think when you are here with this guy, you got rid of this z squared. Now, the only difference is that you didn't really get rid of this z squared by subtracting it. You just approximated your thing on the normal bundle. So maybe it will not look as easy as w is equal w to the 2014 divided by 3, but it will be a perturbation of that. And somehow now you're left with the problem of dealing with this perturbation. And essentially, there is one task which is going to be much easier. That is the task that the final blow-up inherits the singularities of your surface. So somehow you kill that problem. But there is still one problem. So when I told you at the beginning, the magic of the frequency function is that it gives you a model for the kind of small-scale behavior of an area of a minimizer of the Dirichlet functional. You would like to have now something like that even for your approximation of the current on the center manifold. So somehow, what you would like not to have is that the current has an infinite order of contact with your center manifold. So something like sheets which are going like e to the minus 1 over modulus of x squared. Because then you would end up with a function that does not have any Taylor expansion around your singular point. And so when you actually do the zooming, you end up with a trivial function. OK, so essentially, this point, in the case of the harmonic functions, is taken care of by the frequency function. So the monotonicity of the frequency function tells you, actually not the monotonicity, but the fact that the frequency function is finite, tells you that there is a finite order of contact of your graph of the function with the constant manifold, which is your tangent plane, in a sense. So you would like to have something similar here. And what you actually are going to do is you're going to use the following fact. So you compute the frequency function for the approximating map on the center manifold. And since the approximation is almost minimal, you hope to prove that the frequency function is almost monotone. And out of this almost monotonicity, you hope actually to get an upper bound. And once you get an upper bound, you have actually controlled the order of contact, and you can carry on your blow-up argument. OK, so one final remark. So it's even more difficult now to say what's new in our implementation of step 4 compared to him, because we essentially lost track of what he's doing already at step 3. But one very important point is that in our almost monotonicity of the frequency function, we use the smoothed version. And you remember I told you the smoothed version is very nice because at the denominator, I'm taking a bulk integral. So you see, your approximating map might miss a lot of regions of your current. So if what you are actually evaluating is the integral over a sphere, your approximation might completely have missed a lot of spheres in between. And that is going to create a lot of headaches when you actually want to prove a perturbed estimate for your frequency function. So we don't have any of these headaches because we are using the smoothed version. And so both at the denominator and at the numerator, we just have a bulk integral. And now your approximation always misses a set of small measures. So in a bulk integral, that is not going to create a problem. OK, so I think I'm done. Thank you for your attention. OK, so yes. So now this is not Algren-Doe. So this comes out of Chang, which I actually mentioned in the slide. OK, so what you should do is something like this. So first of all, do Chang, which is what we are doing right now, actually a more general version, which we will publish soon. OK, then. Yes, so you get outside, you get actually that your singularities are finitely many. Then you can pick your singularity over there, and then you can approximate it with a multiple valued map. Now, the multiple valued map, you can then use the frequency function to make a rescaling, and you discover that first order for your multiple valued map is these minimizing functions that you can actually classify. And when you classify them, you discover that they are going to be the branching of an holomorphic surface. So that is correct. And somehow this, I should have said, it's already present in the literature. So if you assume the singularity is isolated, there is a paper by Mikalev and White, which is doing precisely this. And actually, the paper of Mikalev and White is showing you something like this. So there might be, at the point, a branching on top of the branching. So then you can kind of try and kind of classify a whole hierarchy of Taylor expansions. And modulo small perturbations, all of them will look like the branching of an holomorphic function. There's a caveat, though. When you actually go through the hierarchies, you don't know that there is a compatibility between the holomorphic structures for each of the expansion. And this seems to be, I mean, when I spoke with Mario, this seems to be a big open problem. So it might actually happen that the first expansion is, looks like holomorphic with one orthogonal change of transformation, and the subsequent needs another change of coordinates.